All right, so earlier we were trying to find the average rate of change of a function over a time interval. We used this example involving a trip to New York. The question now is, how do we find an instantaneous velocity? And so the reason that presents kind of a paradox is that an instantaneous velocity or an instantaneous rate of change is in some sense a paradox, right? Because at an instant, nothing's changing. And so it's strange to ask like a speed at an instant. If you freeze time, what does it mean to talk about your speed at that instant? Because you're frozen. However, if you're in your car and you look at the speedometer at 3 p.m. and then time freezes, you would see some number. So we can answer this question. And so the way to answer it is, again, notice this orange line is a secant line. Its slope. Okay, we know that the slope of the secant line is the average rate of change. We'll use in this case the average velocity. And an average always happens over. So over the time, we'll just use this notation 1 to 5. Okay. What about the instantaneous velocity? So the way we do this at 3, the way we're going to do this is we're going to sort of anchor a point there at 3. We're going to find the slope of a secant line. Okay, so that is another secant line from 3 to 5. And then we're going to move. So I'm just going to kind of indicate. I'm going to start moving this point closer and closer to the green point. Okay, this tends to get messy when I draw it, but like that's going to make a whole bunch of secant lines whose slopes we can find. If you do this limiting process, eventually you're going to get what we call a tangent line. Okay, so gradually, and I'll show you in a second. Okay, but gradually, okay, the slopes approach this. This is called a tangent line. A tangent line, again, it kind of touches in the area the graph wants. It's going in the direction of the graph. And so we're going to see that the slope of the tangent line okay, which we're going to arrive at by doing the, okay, it's like the limit of the slopes limit of the slopes of the secant lines, okay, as we move, let's just call this point P, and let's call this point Q, as P gets closer to Q, okay? That concept is what we call the instantaneous velocity. Okay, at 3 p.m. So let me quickly give you a visual. Here's the idea for a different graph. All right, so like this graph's different. That pink you're seeing there is a secant line. Okay, so the secant line from A to B there is, is indicated by that triangle. The triangle gives you like the rise and the run, but as I start moving it closer and closer, it approaches that red line, which is the tangent line. So we want the slope of that tangent line. Okay, so that's our goal. I'm going to skip this. This is a nice image that kind of just shows you it. As you read across, this is what we're going for. Now, this expression, notice, is very similar to our average rate of change definition. What's different about this, is that we see a variable here. Okay, this is identical to our average rate of change formula, except the second point is varying. Okay, Okay, the second point is varying. This point here is not just b f of b, it's x f of x. Okay, so it's varying, it's changing. All right, let's do one numerical example before we learn how to do it not numerically. So let's take the graph of x squared plus x, okay? And we want to find the slope of the tangent line to the graph of that function at x equals 1. We're going to do it by finding the average rate of change on the intervals 1 to 1.00. So notice how close these 2 points are. We're going to find an average rate of change, but because a rate of change like a speed or velocity doesn't have a lot of time to change in that small window, this average rate of change will be really, really close to the instantaneous. And so we're going to use technology. So we want to compute. So this is like our A and our, our B and our average rate of change. So f of B minus f of A over B minus A in this case would be f of 1.00001 minus f of 1 divided by 1.0001 minus 1. Okay, we're going to use Desmos for this. And again, you're welcome to do this too. Okay, we get 3.00001. Okay, so that's the average rate of change coming from that side. Let's do something similar. Let's instead, again, notice 1 is involved in both cases, but this time we're going a little bit to the left side. So f of B minus f of A divided by B minus A is going to be f of 1 minus f of 0.99999. Okay, and let's see what we get here. I'm just going to go change. Okay, I'm just going to change this to a 1. And then the second value to 0.9959. Except we don't need that. Okay, 2.99999. So that's given us some pretty good evidence. Oops. Okay, so let's go answer the question. Logically, we can see these two slopes are suspiciously close to 3. So the slope of the tangent line to the graph at x equals 1, we're going to say almost certainly must be 3. Okay, I'm saying almost certainly because, it's not like we've proven it or anything, but I think it's pretty clear that the slope of the tangent line is going to be 3 at x equals 1. All right, in the next video, we'll just take a look at how to do this more rigorously, okay? Because the idea here you see is like we've gotten really close, right? We're doing a slope where we've got a value really close to 1, and we could get closer and closer. I think you would see that we would just get more 9s over here and more 0s over here. The idea there that we're capturing is a limiting value. So in the next video, we'll just introduce formally what we're talking about, and we'll do these without Desmos, and we'll do them numerically, not numerically, but with with some algebra skills.